Okay, number 8. A triangle has two sides, A and B. If the angle between the two sides is theta, then determine the value of theta that maximizes the triangle's area. Okay, so it's kind of a general triangle, right? There's no, it's just for any A and B. So let's get an A, and a B, and a theta. And then we'll get a third side. And to get the area of a triangle, we're going to need its height. Although, really, you don't want to. No, okay. All right. So, what's the formula for? Oh, first of all, so what's the domain for theta? Between 0 and, well, really pi, right? I mean, you can lay it out almost flat. Okay. I mean, you can't quite be at 0 or at pi. So theta is going to be between 0 and pi, right? Now, if theta is 0, what's the area going to be like? 0, right? Lying flat, there's going to be 0. And if theta is pi, then it's straight out, and the area will be 0, right? So that's examining the endpoint, right?
Why don't you change your way of getting?
So if theta equals 0, or theta equals pi, then the area would be 0. All right, now what is area, right? Well, it's 1/2 base times height, right? Area is 1/2 base times height. And we're going to look at this in terms of the angle theta. We've got h, the height, and we've got a known side b, right? So what can we say about theta, h, and b? So theta, opposite, hypotenuse, sine theta is equal to h over b. Okay, but we need the height, right? So h is equal to b sine theta. Now, think about it. If we maximize the height, then we're going to maximize the area, right? So if we get the largest height, because the base is fixed. So if we get the largest height, so if we maximize the height, then we maximize the area. So all we really need to deal with is h is equal to b sine theta. And we want dh by d theta, right? So as we change the angle, the height is going to change. And that's going to be equal to, so what's the derivative of the right-hand side? Okay, it's negative, right? B, and derivative sign is negative cos, so negative b cosine theta.
No, it's not.
Oh, right, sorry. You're right, it's positive. B cos theta. All right, so then we're going to get our max when b cos theta is equal to 0, right? Well, okay, should we do the second derivative? I guess we should do the second derivative so we can say. So what's the derivative? Here's where the negative comes in. So that will be negative b sine theta. And between 0 and pi in our domain, sine theta is always going to be positive. negative b sine theta will always be negative, right? So in our domain, this will be negative. In our domain, which implies, so if it's negative, then it's concave down, which leads to a maximum. Okay, so we will get a max when b cos theta is equal to 0, which means that cos theta is equal to 0, which means that theta is so cos, so pi over 2, and 3 pi over 2. But 3 pi over 2 is out of our domain, right? We're only going from 0 to pi. So then cos theta is pi over 2 is where our maximum is, right? We know it's a max. We've checked the second derivative. If theta is 0, we know that the height will be 0 and you'll get no area. If theta is pi, the height will be 0 and there will be no area. So the angle that maximizes the area is theta is equal to pi over 2. So what kind of triangle? Theta is pi over 2. It's a right angle triangle. So a right angle triangle. So the triangle of maximum area is going to be a right angle triangle. Number 9. Determine the maximum perimeter of a right angle triangle, which we know has a maximum area, with a hypotenuse of 20 centimeters. So we know we have a right angle triangle, and we know the hypotenuse is 20 centimeters. So we want the maximum perimeter. So there's going to be an angle here, theta. And in terms of that angle, we can figure out the lengths of the other two sides, right? So what's this length? What's the length of the opposite side? Well, no, because we can't, there's no Pythagorean, right? We don't know. But we can do it in terms of theta, right? So sine theta is opposite over 20, right? So sine theta, which means that the opposite side is 20 sine theta. Okay, so this is 20 sine theta. So what's this side here? The adjacent side. By similar 20 cos theta, right? Do stuff like that in physics and all? I mean, I remember doing a lot of stuff like that in physics. You trying to find, we know this and the side, so we do it in terms of sine theta, cos theta. Okay, no?
Yeah.
Yeah. So what's the perimeter? Well, 20 plus 20 sine theta plus 20 cos theta, right? And we're trying to maximize the perimeter, right? And what's theta going to run between? So what's our, so theta is between, it's got to be between 0 and pi over 2, right? We already have a 90-degree triangle. And we're probably not going to maximize the perimeter at 0 or at pi over 2. I mean, if theta is 0, that 20 is just going to lie on top of there, and we'll end up with 40. And if theta is pi over 2, we'll also end up with just 40. It'll just be It won't even be a triangle, really. But. Okay, so we need to see, can we get a number bigger than 40? Well, so let's take the derivative, this thing we're trying to maximize. So p prime is, okay, we got 20 cos theta minus 20 sine theta. And while we're at it, I think we can do the second derivative, right? It's not that hard to do for this. So what will that be? This will be minus 20 cos, minus 20 sine theta, minus 20 cos theta. So in our domain, what can we say about the second derivative? That's positive, that's just going to be negative, right? So in our domain, p double prime is less than 0, which means that it's, which means that we have a concave down. Okay, so we're going to get a max, right? When are we going to get a max? When we have our critical number or critical numbers. So we want p prime is equal to 0. So 20 cos theta minus 20 sine theta is equal to 0. Divide through by 20, just get cos theta minus sine theta is equal to 0. Yeah, so sine theta is equal to cosine theta. Or you could divide through by cos, right, and end up with tan theta equals 1. Right. Or we also know when sine theta is equal to cos theta, right? It's going to be a pi over 4. Okay. Or tan theta is 1 at pi over 4. So we get theta equals pi over 4. And yeah, really that's it. I mean, we should, I guess, specifically mention that. Okay, so if we did p of 0, which is 20 plus 20 sine theta plus 20 cos theta, we'll get 20 plus 0 plus 20, which is 40. If we do p of pi over 2, which is the other boundary, we get 20 plus 20 sine, oh wait, let's put zeros in there. That's right. 20 sine 0 plus 20 cos 0, and here we get sine pi over 2 plus 20 cos pi over 2, which is 20 plus 0, which is 40. And p of pi over 4. Because it said determine the maximum, so we actually have to find the perimeter, right? So now we do this perimeter. Okay, so this is 20 plus 20 sine pi over 4 plus 20 cos pi over 4. What's the sine of pi over 4 or the cos? Root 2 over 2. So we get 20 plus 20 root 2.
Which would be about 48.
Because I don't know if I wrote.
It's 1.4 or so.
Yeah, exactly. Yeah, root 2 is 1.414. So yeah, 20 times 1.4. What's 0.4 of 20? 1.4 times 20 would be, oh, 48. Bigger than 40 anyways, right? Yeah. We could say this, it's greater than 40, so yeah, that's it. There it is. So that's the perimeter, that's the maximum perimeter. Right. And then what have we got? We've got an isosceles right triangle, right?
from the least significant that it's true.
Determine the dimensions of the rectangle of maximum area that can be inscribed in a circle of radius A. Well, first I'm going to change the A to an R. Because, I don't know, I like R for radius. R is for radius. So we need a circle. We need to inscribe a rectangle.
Really, it'd be a square.
Spoiler alert. I couldn't have said spoiler alert.
Sorry.
Okay, it's gonna be a square. Okay, everybody, it's gonna be a square. Okay, well, let's move on to number 11. No. So the rectangle of maximum, yes, it is a square. So if we, well, rectangle has a length and it has a width. And it's got a radius. And in this case, it's got two radius. It's plural radiuses, radii, two radii. So that'll be 2r across there, right? And we've got L and W and L. So area is length times width. Now, we need to be able to express things, right, in terms of one variable, so be it L or be it W. So, right angle triangle, right, so we got L squared plus W squared is equal to 2R quantity squared. So L squared plus W squared is equal to. So when we do this, we're not actually going to get a number, right? Because we don't know what R is. Excuse me. So if we said AR is 5 or whatever, we get a number, but here we just have a general R. So we're actually going to have a variable R sort of hanging around. Okay, L squared plus W squared is 4R squared. So where you see R, just think that's a constant. Okay, that's a constant. So let's say we solve for W in terms of R, so W squared is 4R squared minus L squared, and W would be the square root of that. Okay, and then we're going to go back to here, and we'll have an expression in terms of L and R, but remember L may vary, but R is a constant. Okay, so just when we're looking at it, R is a constant. That could be some number if we had a value. Okay, so area is L times the square root of 4R squared minus L squared. Okay, so we have it just now in terms of L, right? And so we can do the derivative, so A prime, and we have a product, and yeah, it's just a product, right? Okay, so it's L. Times root of that, so it's 1/2 times 2L. Run out of space. No, I'm just going to start over down here. L times 1/2 times 4R squared minus L squared times 2L. Plus just this, so 4R squared minus L squared to the half, right, times 1. All right, so we can, so here we're going to get an L squared, the common factor. Yeah, remember R is a constant, right? So like 4R squared is like 25 or something.
Power there though?
Oh, you're right. Minus 2L. Okay, so then let's. No, just a half. This is a half.
Well, but it's the whole thing to the power of 1/2. Yeah, but if you derive it,
So if you
Oh,
derive-
that's a negative. Wow.
No, the first one.
the
Oh.
first one.
Oh, here.
Yeah.
Wow.
The other one's still on.
The other one's still 1/2. Come on.
Is it Friday afternoon? No, we don't even have an afternoon class.
If you insist, we can just not do this today.
No, it's fine. Okay, so are we? Let's clean this up then. What have we got? We've got 4r squared minus L squared to the half minus. Okay, so the half, the 2. So we got an L squared, and we've got. Well, let's put it over then. L squared over the square root of 4r squared minus L squared. Okay, well that was pretty painful, so I don't think I really want to do the second derivative here, right? Like, I mean, it's not an easy one. So if they're easy, we do second derivative. So, you know, I guess we'll look at the first derivative test when we get to that point. Okay, so, yeah, we're not doing a second derivative to look at it. So we're going to set this equal to our a prime to 0. We're going to solve. 0, find critical numbers, or determine the critical numbers. Okay, so 0 is equal to, well, let's just put that under a root sign. Okay, so if we move the negative term, right, if we just add this to both sides, so we get L squared over square root of 4r squared minus L squared is equal to the root of, put that over 1. Okay, so we can just multiply both sides by that square root and get L squared is equal to just 4r squared minus L squared. Okay, because we're squaring the square root. So 2L squared is 4r squared, and L squared is 2r squared, and L is root 2r. Squared, so root 2r. Okay, so the length is root 2 times the radius. Now, we've got to figure out, is that a maximum, right? Well, what's, so the length and the width are anywhere from 0 to 2r, right? I mean, they could be running along here. So 0, okay, so length and width are anywhere from 0 to 2r. If the length is 0, then the area is 0. If the length is 2r, then the width is 0 and the area is 0, right? And same thing for the width. If the width is 0, the area is 0. If the width is 2r, the length is 0, the area is 0. Okay. So between 0 and 2r, 0 and 2r, somewhere in between there is root 2r. And what we want to figure out is this, positive or negative. So what we could do is, if we look close to 0, well, actually 1r, right? What if we just took r? So r would be in here, right? So if we stuck an r in there for L, we'd get 4r squared minus r squared. So we'd have the square root of 3r squared here. And here we'd have r squared over the square root of 3r. We might want to write this down. So if we chose in this interval, right, because we can't really choose a number. I can't say, hey, let's put a 1 in there. But, well, we could, but no. We'll say root 2r. So let's say we choose r. So a prime at r will be 4r squared minus r squared to the half minus r squared over 4r squared minus r squared square root square root. So it'll be 3r squared minus r squared over the root of 3r squared. If we stuck that all over the root of 3r squared, this would be 2r squared. Okay. And then, okay, this is going to be positive, right? So this will be positive. So then A would be increasing. And if we take something close to 2r, then this will be like 4r squared minus something just under 4r squared. Okay, so it'll be very small, r squared, minus larger r squared over, so this is very small, this will be bigger, this will be negative. Okay, so we will have a maximum. Okay, so max. And that's it, right? Oh, well, it's a dimensions though, right? So we worked out the length, so we got to go work out the width, so the width is here. So when L is equal to root 2r, then W is the square root of 4r squared minus 2r squared, right? Because L squared is just 2r squared, which is the root of 2r squared, which is root 2r. So Jared, what shape could this possibly be if the length and width are the same?
Diamond.
Diamond. A rhombus.
No.
It's all how the circle rolls. They have that, didn't they have that, the square-shaped checks and the diamond-shaped checks? Isn't a commercial for breakfast cereal, the square, but they said, or shreddies,
Yeah.
was it shreddies? Yeah. The square-shaped shreddies and the diamond-shaped shreddies? All right. What are the questions? Determine the dimension. Okay. So then let's come up with a statement. The dimensions are. Root 2r by root 2r. Okay. Length, width, square. It is always thus. The rectangle of maximum area is a square. Next up, determine the angle theta that maximizes the area of the trapezoid shown below. Trapezoids. Okay. It's got 5s. At one point I changed it to 10s. It makes the numbers slightly, but it's no real difference. I mean, yeah, we could do it with 5. All right, what's the formula for the area of a trapezoid? Well, probably on your sheet. It's 1/2 a plus b times h, where h is the distance between the parallel sides. And A and B are the lengths of the parallel sides.
No, there is a very, very long trapezoid rule, but that is not on there.
Not a trapezoid, it's just the area. They don't have area of a
They
trapezoid?
do not have area of a trapezoid.
Figure out the area of the trapezoid.
Yeah.
Yeah.
Yeah. If you could just take this and, make that right. I think actually if you cut this off of here and then move it over there.
That's
Yeah.
what
Yeah, that's.
I did. It bounced.
Yes, yeah, I know. Smart did something. One nice thing. Okay, so that's going to be our height. That's 5. That'll be a height. That'll be a height. This will be 5. Excuse me. So we need expressions before the height. So in terms of theta and the 5, then what's the height?
Sine theta is equal to h over 5.
Yeah, sine theta is h over 5. Sure, put this down here in our little. So sine theta is h over 5. So then h is 5 sine theta. Okay, and maybe we'll just leave this here because I got no room up there. I guess we can write it here. So 5 sine theta. Then what's this distance here? Or down here? So if that one's 5 sine theta, then the other one is 5 cos theta. 5 cos theta. And then up here, also 5 cos theta. Okay, and then, what? Oh, yeah, sure. Okay, and so that is our B. All right, so we can fill stuff in, right? We know A is 5, we know B is 5 plus 10 cos theta, and we know H. Okay, so area is 1/2 times, let's put the H in front, so 1/2 times H, 5 sine theta, times A plus B, so 5 plus 10 cos theta. All right, so we got 5/2 sine theta and 10 plus 10 cos theta. And if we multiply that in, 2 goes into that 5, we'll get 25 sine theta plus 2 to 5, 25 sine theta cos theta. I could say, but wait a sec, I've seen that sine theta cos theta before, right? So then, you go 25 sine theta plus 25 halves sine 2 theta. Okay, and that will be relatively easy to take the derivative of, right? Remember, sine 2 theta is 2 sine theta cos theta. So if I just divide this by 2 and then turn that into sine 2 theta, right? It's easy. You don't want to do the derivative of this, right? It's a product and blah, blah, blah. I mean, here it's chain, but it's just a 2. What was that? That was A. So, excuse me, then we can do A prime. So, derivative of 25 sine theta is 25 cos theta. Plus, okay, so derivative of sine 2 theta is going to be 2, so there's going to be a 2 multiplied by a 2, so we'll just go 25 over 2 times 2, just get 25, right? So going slightly out of order, so 25, and then the derivative of sine 2 theta is going to be cos 2 theta. Okay, so normally I'd say it was cos 2 theta times 2, but then I've got the 25 over 2 times 2, so just 25. All right, well, we can do the second derivative now, right? That won't be too hard because it's no harder than what we just did. So we'll do that over here. So derivative of 25, that'll be minus 25 sine theta. And the derivative of cos is minus sine, and we're going to have a 2, so it'll be like minus 50 sine 2 theta. Oh, and I guess we should go back up here and say something about theta, right? So theta is going to be between 0 and pi, right? I mean, we could do that, or we could fold it all. But it's not going to maximize the area, right? And at 0 or pi, those areas are going to be 0, right? So if theta is 0, then our height is 0. You might say, if theta equals 0 or theta is equal to pi, then h is equal to 0, which leads to a is equal to 0. Okay, so we've done the boundaries. Okay, sine is going to be positive. So this Well, wait a sec. I mean, the sine, if we go sine 2 theta, so we might have to look at a double prime at the angle we get, right? Because sine 2 theta could be positive, could be negative between 0 and pi. Right, as soon as we go over pi, so any angle over pi over 2 would give us a negative. So, okay, so keep this here for now. So we want to set this equal to 0, right? So critical number. Okay, so we got 25 cos theta plus 25 cos 2 theta is equal to 0. Cos 2 theta, right? So we can go and we can replace that, right? There's what, a 2 cos squared theta minus 1? So that'll give us a quadratic in cos theta. And lots of 25s, and 25 cos theta plus 50 cos squared theta minus 25. Okay, so let's rearrange and divide by 25 all at the same time. So rearranging, we'll put this front 2 cos squared theta plus cos theta minus 1 is equal to 0. Okay, so arranged in descending powers of cosine and dividing by 25 at the same time. Factoring 2 cos theta and cos theta. So it'd be plus 1 minus 1. Two cos squared plus 2, yeah. Okay, so 2 cos theta minus 1 equals 0. So cos theta is a half. And between 0 and pi, that's only going to happen once, which is where? Pi over 3. Yeah, so theta is pi over 3. And cos theta plus 1 is 0. Cos theta is negative 1. 3 pi over 2. Okay, and that's out. Oh, pi. Pi. You're right. Okay. All right, which we can reject anyways because we already said if theta is pi, then the area is 0, right? So we don't need to look at that. So we do need to look at a double prime at pi over 3. Which is equal to negative 25 sine pi over 3 minus 50 sine 2 pi over 3. Okay, sine pi over 3 is positive. Sine 2 pi over 3 is positive. This whole thing is negative. So it's concave down, so it's a maximum. Okay, so equals negative concave down max. So we have a maximum area. Did it ask what the area was? Nope, just the angle. So a maximum area. So the trapezoids. Maximum area occurs 1C and 2R. Is that right? Is that right?
Happens.
Can't spell. So maximum area when the angle is pi over 3. Right, determine the angle that, yeah, and we actually answered the correct question. Okay, last one. The infamous ladder down a hallway problem. Pipe around a corner. So you're walking a ladder down a hall, and you got 2 different widths of hall, and you want to say, well, what's the longest ladder that I can get through, right? We're going to walk this ladder, and we're going to try and turn, and at some point it's going to jam. right? If it's long, too long, you just can't turn it. Okay, and we're going to assume this is the ideal ladder of no thickness, right? It's just a line ladder.
Sound like it has very good support.
Yeah.
How'd you stand on
You could also do this with a pipe. So just basically carrying any long, inflexible object down a hallway and saying, so what's the longest one that we can get through here? So starting with, of course, a diagram, right? We need a diagram. So we've got one hallway which is 4 feet wide meets another hallway which is 8 feet wide. Okay, so let's do 8 feet wide and 4 feet wide. So I have an 8-foot wide hallway here. And I've got a 4-foot wide hallway here. And we've got a ladder which, when we go to turn it, is going to end up like this, right? So there's the ladder, and if it's too long, we can't turn it through the hall. All right, so we have a ladder of length L. And there's going to be some angle here, theta. And that angle there will also be this angle here, right? So we'll call this distance A, and we'll call this distance B. And what we need is expressions for A and B in terms of theta. And the sides, right? So we know this is 4, and we know this is 8. Okay, theta, B, and 4. What's the relation? Yeah, so sine theta is B over 4. Sine theta is, sorry, it's not B, it's 4 over B, right? Sorry. Okay, so that means that B is equal to 4 over sine theta, or B is equal to 4 cosecant theta. So secant theta. All right, what can we say about A and theta? And these guys are 90. Right? So theta, so Jason, so cos theta is 8 over A. So A is 8 over cos theta. So A is equal to 8 secant theta. Now the length of the ladder, which is the thing we want to maximize, right? So the length of the ladder is A plus B, which is 8 secant theta plus 4 cosecant theta. All right, well, we want to maximize it, so we take its derivative. The derivative of secant is secant theta tan theta. And the derivative of cosecant is cosecant cotangent.
Negative cosecant cotangent.
Negative cosecant cotangent. Thank God for formula sheets. Okay, here's where the trick comes in. Or here's where the trick comes in. Yeah, I know, that was bad. What we're going to do is that we're going to multiply through. by sine theta tan theta. Oh, well, first let's set it equal to 0, right? Okay, okay. We're not going to do the second derivative, right? Second derivative, no. Okay, so critical number, L prime is equal to 0. Okay, so 8 secant theta tan theta minus 4 cosecant theta cotan theta equals 0. Okay, so here's the trick then. We're going to multiply both sides by sine theta tan theta. Okay, so why would we do that? Well, the sine theta is going to take this out, and the tan theta is going to take this out, right? So this is 1 over sine. So we're going to multiply both sides. Sine theta, tan theta. Okay, so sine theta is going to take this guy out, tan theta is going to take this guy out. We're just going to end up with a minus 4. The right-hand side is 0. So secant theta, well, secant's 1 over cos. So we multiply the secant by sine, we get sine over cos, which is tan. So now we have tan theta times tan theta, right? So this becomes tan theta, this is tan theta, and this tan theta. We get 8 tan cubed theta. Okay, and then this can actually be solved, right? So we get 8 tan cubed theta is equal to 4. Or tan cubed theta is 1/2. Which means tan theta is the cube root of 1/2. Or tan theta is 1 over the cube root of 2. All right, so how does that help us? Well, first, we want to figure out if we have a max or a min, right? So let's go over here. We'll do the first derivative test. So 0, and pi over 2. So if we go back to here, the angle, right? So theta is going to be between 0 and pi over 2. Right, so in other words, you could have it flat here, and just walk it into the wall, or you could have it walking this way. But if you're walking it this way, it can only be 4 feet wide, and if you're walking it this way, it can only be 8 feet wide, right? You're going to go smack, and then it has to be 8 feet wide. You can just take it through here. So we would need something between 4 and 8. Okay, so maybe here we just say, so if theta equals 0, then we get 4 feet wide. And if theta is equal to pi over 2, then we get an 8-foot wide ladder. All right, so somewhere in between 0 and pi over 2 lies our theta, which is the inverse tan of 1 over, so we don't know what theta is, right? But we do know it's between 0 and pi over 2. So what we need to do is just sort of figure out what we're doing, L. So if we're really close to 0, so if theta is really close to 0, then will this be a positive or negative?
It would be positive.
Yeah. And if theta is really close to pi over 2, then will this be positive or negative? Be negative. Increase, decrease, max. Okay. So, algebraically we've shown there will be a max. But, how do we get that max, right? Like, where do we go? Well, if we look at our number here, so we have, here, let's pull this up here. So we know that tan theta is equal to 1 over the cube root of 2. Now, we're going to go to x, y, and r. So in terms of x, y, and r, what's tan theta? Just think of an x, y, r thing, right? Triangle. Right? Just back to first principles of sine theta is y over r, cos theta is x over r, and so on. Okay? So tan theta is y over x, right? So tan theta is y over x. So that means that y is equal to 1 and x is equal to the cube root of 2. Right? So then we can use that to get r. Now, once we've got r, then we know x, y, and r, which means we can get secant theta and we can get cosecant theta. Right? Because what's secant theta? It's like r over x. And cosecant theta is r over y. Okay? So we got x and y, we need r. So we know that r squared, or r is the square root of x squared plus y squared. So r is the square root of x squared plus y squared, which is the square root of the cube root of 2 squared plus 1 squared. So the cube root of 2 squared is 2 to the 2/3 plus 1. So that's our r. Our r. That's funny, our r. That's our r. And we want the length, right, which is 8 secant theta plus 4 cosecant theta. So length is 8 secant theta plus 4 cosecant theta. Okay, so the secant of theta is x over, or sorry, it's r over x. So it's the square root of 2 to the 2/3 plus 1 over x, which is the cube root of 2. So that's the secant of theta. And the cosecant of theta is r over y. So that's just going to be 4 times the square root of 2 to the 2/3 plus 1. Now we could simplify it. We could factor out a 4 times the square root of 2 to the 2/3 plus 1. So I will, just for heck of it. So 4 square root 2 to the 2/3 plus 1 times 2 over cube root 2. So a little over 16.6 feet. Which is greater than 4 and greater. So that's our maximum length of ladder. So you could get a, I'd say to be reasonably safe, you could get a 16-foot ladder around that corner. Okay. Even 16 and a half. You're likely going to ding the walls. So add the end of your ladder. So we're asked to determine the length of the longest ladder, so the length of the longest ladder.
If you have a 4-foot ladder, and you put it at this angle.
16. I don't want to round that up, it'll get too long.
The question is what?
I know,
Period.
but we could do better.